All right, our next topic in Chapter 2 is nomenclature. In other words, naming molecules. Okay, so quite often you'll be faced with situations where you have to take the name, the written name of a molecule, and come up with a formula for it, or vice versa. And so we're going to start with what are referred to as binary ionic components. Molecules, that is. Binary ionic molecules. Binary meaning two things, so just two elements. Ionic meaning that we are dealing with a metal and a nonmetal. So the way the names generally work for binary ionic is that you have the metal name unmodified plus the non-metal base plus IDE. Okay, so pretty straightforward. So for example, if I have NaCl, the metal is sodium, so I just give the sodium the metal name, and then the nonmetal is chlorine. The base of that name is chlor, and then I add the IDE, so sodium chloride. All right, so let's do another one, MGS. Okay, binary, there are two things there, only two things. It's ionic, I have a metal plus a nonmetal. So I'm going to say the metal's name, which is magnesium, and then the base of the nonmetal is sulf, for sulfur, sulfide, IDE. So magnesium sulfide. KF. All right, two things there. Potassium's a metal, fluorine's a nonmetal, binary ionic. All right, so I'm going to give the name of the metal, which is potassium. And then the base of the nonmetal is fluor, fluorine, fluor, and then IDE, fluoride. Now we can also do binary ionic using transition metals. Transition metal binary naming. Okay, so transition metals can have more than one cation. So transition metals can have more than one cation. Right? So for example, magnesium, sodium, potassium in our previous examples, they all only make one cation. Sodium makes a +1 cation, magnesium makes a +2 cation, potassium makes a +1 cation. That's all they do. Okay? But some of our transition metals, and this is partly why I refer to the transition metals as the wasteland of weirdness, many of our transition metals make more than one cation. So for example, iron can be a +3 cation or a +2 cation. Copper can be a +1, or we can have copper be a +2. Vanadium, which is my second favorite element, vanadium can be a +2, a +3, a +4, or a +5. All right, and that's all of those different cations that it makes has to do with, contributes to the fact that it makes multiple beautiful shades of green. Okay, so, but regardless of that, the deal with these multiple cation metals, we can apply the same reasoning to the naming, but we use a Roman numeral to denote which metal cation we're dealing with. Okay, so for example, if I have iron 3+, I'm going to say iron 3 using a Roman numeral. Right? If I'm talking about vanadium 5+, vanadium, and I'll use the Roman numeral for 5. Right? So the tip that I can offer when you're trying to figure out what is the name, use the anion to tell you. Right? So for example, if I have VO, right, that's vanadium plus oxygen. Oxygen makes a 2- anion. In order for this to be neutral, the vanadium must be 2+. 2+, 2-, everything comes out neutral. That means that the name for this, we still use the same strategy. We use the metal name, the anion plus IDE, but we put the Roman numeral in there. So this will be called vanadium 2 oxide. Ox is the base for oxygen, oxide. And this video is reminding me to make another video to talk about how to determine what ions are what from the periodic table, but that's for another video. Let's talk about another example. Let's say I have Cu2S. Okay, sulfur is another 2- anion, right? If I have 2 coppers, both of those coppers together need to equal 2-, right? Need to balance a 2-. So that means that each of my coppers is a 1+. All right, 1+, 1+, that makes a 2+ together, balancing a 2-. So the name for this compound is still, like I said, the same strategy. We say the name of the metal, the base of the anion with IDE, but we put the Roman numeral in there because it makes copper's one that makes multiple ions. So copper 1 sulfide. All right, so continuing on, let's talk about binary molecular or covalent compounds. Okay? So we're talking about non-metal plus non-metal, right? So what we do is we use prefixes. to tell us how many atoms. Right? So our prefixes are based on the Roman prefixes. So we have mono equals 1, di is 2, tri for 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. Right, so you might recognize a few of those at the end of that number set. So hepta, octa, nona, deca. So if you think about the months of the year, this is a bit of history trivia for you. Once upon a time, there were only 10 months in the calendar year. Hepta, septa, September was the 5th month. The 7th month, not the 9th month. Octa, October, used to be the 8th month. November, nona, that no part, used to be the 9th month. Deca, December, used to be the 10th month. And it wasn't until the Romans came along and we had a particular set of Caesars, Augustus and Julius. They came along and decided that they needed months named after them. So the months of July for Julius Caesar, August for Augustus Caesar were added to the calendar. And so now the names for the months of the year, at least at the end of the year, no longer match their numerical counterparts. But anyways, I digress. I love history, so this is what happens. So the way this works is that we use prefixes to tell us how many of a particular element are in the compound, with the stipulation that if the first element is 1, we omit the mono. Right? Anything past the first element, we have to say mono for that particular thing if there's only one there. So let's do a little practice. So let's say I have the compound CO2. Right? So we say there's one carbon, but it's the first element. So I wouldn't say monocarbon because it's the first element. So I just say carbon, leaving out the mono part, that's 1, dioxide. Right, so I say di for 2, the base of that second thing, and then IDE. Right, so di meaning 2. 1 carbon, 2 oxygens. If I have N2S3, right, now we're not dealing with just one atom for the first element. I have 2. So I would say dinitrogen, di meaning 2, and then trisulfide. Right, tri meaning 3. There's 3 sulfurs there. Right, so it's very similar. The second half of the name is very similar to the way the ionic compounds work, where we use the base of the word and then that IDE, but we put in this extra bit of what is the prefix. Right, my personal favorite, H2O, dihydrogen monoxide. Okay, so I use the mono part, but I combine it with the word oxide, and rather than saying monoxide, I just combine the O's. Okay, it's a little convention thing. But if you ever want to weird somebody out that is not science-minded, try to convince them that dihydrogen monoxide is dangerous. Okay, maybe say like breathing dihydrogen monoxide will cause death, which is true. So I'm going to stop this video right here before we go on to more naming, and we'll come back with talking about acids.